Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to start analyzing data with a normal likelihood in a Bayesian manner, of course. The prior that we will consider is a discrete prior, and we are going to have an additional assumption. Okay, we're going to make an additional assumption that we know the value of sigma squared. Okay, let's begin. If you remember, right, in another video we talked in detail about the likelihood function of a sample coming from a normal distribution. Okay, so let me remind you what the likelihood function looks like for that sample of size n. Okay, so for a sample, so we could think about that as conditional probability, the probability of observing particular values for y1, y2, so on up to yn, given that we have particular values as well for the two parameters mu and sigma squared. Okay, so what we did is that we came up with an expression and we used the proportionality symbol where we separated the two statistics, right, the two functions of the data that are going to be relevant to say something for the variance and for the mean. Okay, so what we ended up with was an expression that looks something like this, right? So we have sigma to the power negative n times an exponential, right, to the power minus n minus 1 times s squared, where s squared represents the sample variance divided by sigma squared times an exponential to, and that exponent that we're going to have here, right, involves both mu and sigma squared. So we have e to the negative n times mu minus y bar squared divided by 2 times sigma squared, and here we also have 2 times sigma squared. Okay, that's better. Remember, we derived that expression in detail. Okay, so we said that at the beginning of this video that we're going to have an additional assumption that sigma squared is known. Okay, so let's just point that out here, that for sigma squared known, the likelihood function can be simplified. So now, since we're assuming that sigma squared is known, right, we could forget about the first term, right? That one doesn't involve mu. And we could absorb that term with the proportionality symbol. Okay. So now let me just make a couple of additional observations about this expression here. So note that that expression is equivalent to the following expression. We could be dividing by n here. Sigma squared divided by n is the same as this. You guys agree? Okay. Something more. Mu minus y bar squared is the same as y bar minus mu squared, right? So these two expressions are the same. Okay. Now, furthermore, note that the information contained in that sample, that set of observations y1, y2, and yn, right? Well, guess what? We only need y bar to reflect the information contained in that sample. So we could think about this as an expression that depends on y bar alone. We don't need to know the individual values. If we know what the sample mean is, the sample mean contains the same information as the entire sample. Okay, this will be useful for what we're going to be doing next, okay, to analyze that sample using a Bayesian manner. What we're saying is that the likelihood of the entire sample is equivalent to the likelihood of y bar. And the other two observations that we made here also are going to be useful, because take a look at this expression here, right? This should remind you of the kernel of a normal with mean mu and variance sigma squared divided by n if the variable is y bar, right? So what we're saying here is that to evaluate the likelihood of an entire sample, all we have to do is to evaluate, right, a normal with mean mu and variance sigma squared divided by n at the point y bar, the sample mean. Okay? Okay. So now we are ready to start discussing that example where we use discrete prior. So example. So suppose that we have a random sample of 4 observations from a normal distribution. Okay, so what we have here is something like this. We have y1, we have y2, we have y3, and we have y4. Okay, and these guys come from normal with mean mu unknown, but we assume that sigma squared is known and that it is equal to 1. Okay, now the values are the following: 3.2, 2.2, 3.6, and 4.1. Okay. Now, let's talk about those values that we are going to be considering for the parameter mu. Okay, so it's a discrete prior, so meaning we're just going to be considering a finite number of values for our parameter mu. So we have mu, and the parameters that we're going to be considering for mu are 2, 2.5, 3, 3.5, and 4. Okay? Then we need our prior. We are going to be using a uniform prior. We're going to assume that each of these 5 values are equally likely. Okay, so 1/5 or 0.2, if you will, for each of these guys. We know that if we're going to be using this tabular format to apply Bayes' theorem, what we need to do here is to have the likelihood. Once we have the likelihood, we have prior times likelihood will be your next column, and once you have the product between prior and likelihood, what you do is you do the sum of all these products, and then your posterior would be each of these guys, each of these products divided by their sum. Okay, that is going to yield the posterior. So, as we said here, we could evaluate, instead of, since we're interested in finding the likelihood of that sample, right, of 4 observations, we could just evaluate at y bar. So we're going to need to compute y bar, and then evaluate at the value that we're proposing for mu, in this case for each of these values, 2, 2.5, 3, 3.5, right? And once we have that, we just multiply, prior times likelihood gives you this guy, prior times likelihood, and so on, right? You add them up, you divide those cross products by the sum, you have your posterior. Make sense? Okay, but instead of using that tabular format, let's use R. If you have a chance later today, do this, okay? Do it using your table, and you'll see that this approach matches what we're going to be doing using R, okay? But the important thing here is that evaluating the likelihood for an entire sample is equivalent to evaluating the likelihood of y bar, and the likelihood of value of y bar is just evaluating y bar at the PDF of a normal with mean mu and variance sigma squared divided by n. Okay? So now let's do this using R. So let me use let me call it X to refer to the entire sample, okay? A vector that contains the entire sample. And what we said in this case is we have 4 observations, and they have the following values, right? 3.2, 2.2, and so on. Okay, so Let me use x to refer to that vector that contains our 4 observations. So 1, 2, 3, 4, great. Okay. Now, let me create an object called mu.prior. That guy will contain the values that we are considering possible for our parameter of interest. So 2, 2.5, 3, 3.5, and 4. So 2, 2.5, 3, 3.5, and 4. We are considering 1, 2, 3, 4, 5 values. Okay. Now, prior, that object will contain the probability for each of those 5 values that we're considering. Since we are going to be using a uniform prior, let me repeat 1 over 5 times, right? Let me make sure that it's what we want. It is what we want. Great. Now, we know that the likelihood, right, is the same as evaluating the mean y bar, the sample mean, for a normal with a mean mu and variance sigma squared divided by n, right? So from the table we can see that we want to evaluate that for 5 different values of mu, right? So we know that we can use the dnorm function to evaluate the PDF of a normal, right? The syntax is you need the value where you're going to be evaluating, then the mean, the parameter mu, and then the standard deviation for that particular normal, right? So we're going to be using these different values of mu, and the variance is going to be sigma squared divided by n, but we need the standard deviation. Since sigma is assumed to be 1, we are going to have sigma divided by the square root of n. That's going to be the standard deviation of this guy, right? Instead of sigma squared divided by n, we're going to have sigma divided by the square root of n, okay? And we're going to evaluate, okay? So here we go. Let's use dnorm to do that evaluation. So dnorm, we're evaluating at the mean of our vector x, that's the mean for our sample. The parameters mean, we're going to be evaluating at these 5 different values. So mu prior. Standard deviation, as we said, we're assuming that sigma is 1. We have a sample of size 4, so we have sigma divided by the square root of n, okay? So as you can see, we have 5 values. Those would be the 5 values that you would place here. Then you would do the product, then the sum of those products goes here. Each of those cross products divided by the sum is going to give you the corresponding posterior. Make sense? Okay, so here we go. Let me just save this. Let me call it likelihood. Okay, so now what we know is that posterior is going to be just prior times likelihood divided by the sum of those cross products. Okay, so our posterior is a vector with 5 elements. That would be the last column, right? And we can check that it is a legit probability by computing the sum, it should be 1. It is 1, right? And each of those numbers is a number between 0 and 1. So it is a legit probability distribution. Okay, so that's just using R. Okay, now we also know that the authors of our textbook created an R package, a library, right? So let's try and compare what you would get if you used that library, that R package. So first, I am assuming that you already installed the R package bolstat, right? And here I'm just loading it, okay, because it's not part of R. So every time that I launch R, it's not going to be there for me. So if I want to use it, I have to load that R package, that library, okay? But the installation, you have to do that only once, okay? So now the function from that library, from that R package that we want to use in this case is norm dp, which stands for normal with discrete prior, okay? So here we can see the syntax. So we need here x. This would be just a single observation or a vector of observations, right? Sigma here, sub x, right, is giving you the well, here what you need is the value of the standard deviation that you're assuming, right? In our case, we have sigma squared equals 1, which means that the standard deviation would be 1 as well, okay? So since we're assuming that, you know, sigma squared is known, okay? Okay, so then we have the other argument here, mu. Mu is going to be the values, the possible values, right, for our discrete prior, and this gives you the probability for each of those possible values. Make sense? Okay, so let's try and give it a shot. Okay, so we already have x, that's our guy, right? That's our sample. We already know that standard deviation is 1. Our possible values, mu. Oh, yeah, we don't have that one, right? Oh, that would be mu prior, right? 2, 2.5, 3, 3.5, and 4, right? And then we have prior. Okay, so we have mu prior and prior. That's what we want. Okay, so here we go. Let's see if that works. So norm dp, right? We have x, we have 1, we need mu, which is the vector of possibilities, and for this one we have the vector of possibilities is mu prior. Mu equals mu prior, and then here for mu prior we have prior, right? This one contains those guys, 0.2, 0.2. Let's see. Okay, so here we have a graph, right? But let me save this in an example, well, in an object called example, okay? So we can see all the results. Okay, So that's the posterior, right? 0.015, 0.12, 0.35, 0.36, 0.14, right? Okay, now let's compare this, right? So let's see example, $sign posterior, that's what we have, and ours, it's called just posterior, right? When we did it without the help of the R package. So we can compare. Oh, there's a difference here. I wonder why that is. Let's do something here, right? So note that what we did here is we have, let's be consistent with what that function is using. So x, yeah, no problem. Let's use x. That's okay. Let's see, instead of mu prior for this one, let me change that just to mu. So we are consistent with the way they define their function here. So mu would be just the values, right, for the R package. Now for mu prior, let's do this, right, 1/5, 5, right? Okay, so okay. So now let's try and do the same thing, but now we're going to have the same names that you would have here, right, to avoid any sort of misunderstanding between this function from the library and then the way that we named our objects. Okay, so here we go. So it would be norm for discrete prior x, we have 1, we have mu, which is the possible values, these guys here, and then we have mu prior. Now they have the same names, right? Because maybe that's why we ended up with something different. The only thing that we want is the posterior, so we use that dollar sign and then the name of the object we want, posterior, right? That's what we have here, right? So 0.015, 0.12, 0.35, 0.36, 0.14. Now let's do something like what we did before, right? With without the use of the library. Here we go. So what we need is to evaluate our likelihood. So our likelihood would be just evaluating a normal at the sample mean. The mean that we're going to be using is just mu, right? And then, well, it would be, yeah, it would be mu, these possible values, right? 2, 2.5, 3, 3.5, and 4, right? The standard deviation that you would use would be 1 over the square root of 4. Okay, so now what we need to find the posterior, just using Bayes' theorem, would be your mu, right? The values of mu. So posterior would be values of it would be prior, right, times likelihood. So we would have mu prior times our likelihood divided by the sum of that. It should give you the same thing. So now let's compare posterior. There we are. So same thing, right? 0.015, 0.122, 0.35, 0.36, 0.14, right? So the only thing was, because of the names that we gave to our vectors here initially, when we applied this, when we used that norm NDP function, then there was a confusion there between that function and R. Okay, so anyway, can you see that we can do it, just with plain R, just kind of using that tabular approach, and we can also do that using the norm discrete prior function from the bolstat R package, okay, and it gives you the exact same results. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.